RF Man here. Today I want to continue my discussion on how to design, build, and test an RF amplifier. Of course, the amplifier that we're speaking about is the one I presented in part 1 of my videos. And I mentioned in part 1 that we were going to use a circuit simulator called LTSpice to measure input impedances. So I'm going to start the video by just providing some information on where you can go to download that software. So LTSpice is available from Analog Devices. So you just need to go to analog.com and from their home page, search on LTSpice. You'll get to the download page, which is what you see here. And if you scroll down to the bottom, you'll see the links to download the software. There's versions for Windows 10, for Mac OS 10, and then later versions of Mac and Windows. Some of them are still supported, some of them are not. So you can pick one that matches your system. It's easy to install, doesn't require that much disk space, and as I mentioned in the first video, it's very user-friendly. This has been around for probably 3 decades now. It's been updated and refined. In the old days, simulators were hard to use, but today they're relatively simple. So I'm going to demonstrate a couple of circuits and show you how to measure input impedance of each of those circuits, and also discuss a couple of examples that show impedance transformation using a transformer and using the turns ratio in the transformer. So why would we use a simulator? Well, my experience, and I've been using this particular simulator for a few years now, it's really a very useful tool. It can help you design and test before you actually build a prototype and start your bench testing. So it does save a lot of time. You can do a lot of experiments with your circuit. You can change component values. You can change inputs and output impedances and all kinds of experiments to see the effect. And it will help you learn for sure. So that's where you get it, Analog Devices. So after you do your install, you're going to get a shortcut on your screen here. And you just open up the software, double click, and that's what the startup screen looks like. And from there, you can go to File and open an existing project or start a new project by clicking New Schematic. And there's your workspace. So what I'm going to do is I'm going to start out by setting up a very simple circuit using a sine wave generator and a 50 ohm resistor. So here on the top, you see all the different components that are available: capacitors, inductors, resistors, diodes, transistors, etc. There's logic circuits, just about any kind of device you can think of. And there are models readily available on the internet. The PSpice models are compatible with LTSpice since they're both based on the Spice software. And there's lots of examples on the internet. You can search, there's hundreds of videos, there's all kinds of projects and circuits and a lot of information. Like I said, it's user-friendly, so we're going to just jump right in here and design a simple circuit and show you a couple of things. So components, we use this symbol, click on that, and I want to get a sine wave source, so we put in sine, and there's our signal generator. So it'll automatically create another symbol. To get out of that, you just do a right click, and then you can size this symbol and reposition the symbol. So to reposition, you just click and drag. It'll drag the whole schematic or one individual device. And also to size it, you just use your mouse wheel here, and you can make it larger, as you see there, and you can make it smaller. So I'm just going to go ahead and kind of fit this in and maybe make it a little smaller. Yeah, that looks pretty good. Okay, so there's our signal source. And what else do we need? A resistor. So you click on the resistor and drag and drop. And like I said, it's going to create a second resistor. Just right click to exit out of that. And then we have to wire our circuit. So this is fairly easy. This is the wiring tool up here. And we just click on that and we get a cursor. And then to wire it, we click and position the wire where we want it. Click again, position it, click. Now you can go right through the component, which makes it a little faster and a little more efficient. Click and click and click. Okay, and then to get out of it, you just right click your mouse and there's our simple circuit. So what do we want to look at here? Okay, we want to basically run the circuit and measure the impedance. So we'll start by setting up the sine wave generator. You just mouse over the component and you see the pointer there, and you do a right click and you'll see there's some default values in here. So we don't want any offset voltage. We're going to keep the amplitude to 1 volt. We're going to be able to sweep this up to 30 megahertz. So megahertz can either be MEG or what we're, I guess, more accustomed to might be MHZ. And this uses all the notations that we're already familiar with. For example, for microfarads, it's UF, microhenries, it's UH, nanohenries, NH, etc. So those should be familiar to you. And again, we put 1 volt in here for amplitude. And then we want to give this a 50 ohm series resistance. Like most of our RF equipment on our bench, it's going to be 50 ohms. Okay, so there's the parameters for the sine wave generator. Now you can use this drag tool up here and just click on that, and that'll allow you to reposition. So if I want to reposition this, kind of get it out of the way for me, click, drag, click, click, drag, click. Okay, so now it's out of the way. I got a better view of my circuit. Okay, to get it out of that, you just right click. Okay, now we want to change the resistance value to 50 ohms. We mouse over the resistor, we do a right click, and you can see we can enter the resistance, the tolerance, and the power rating. There's other properties too, depending on the resistor, but all I'm interested in right now is the resistance value. We're going to make that 50 ohms. Okay, so there's my simple circuit. I'm going to just reduce the size of this a bit. Okay, so now there's a couple of things we can do to simulate the circuit. Okay, we click on simulate, and this is the button that's used to edit the simulation commands. And we can do a transient analysis, which will just allow the circuit to run for the period of time that we specify. And I'm going to start with that just to show that the circuit's working. And we can also do an AC analysis. This is what we use to measure impedances and other parameters. And then you can see there's a lot of other features in here, different types of analyses that can be done. So it's a very powerful tool. So we're going to go ahead and start with the transient analysis just to run the circuit. So we have to enter a stop time. We have to enter a start time and also the steps in between. So let's put the stop time at 60 microseconds, and you can go US or U. Okay, we'll delay 10 microseconds for starting, and we'll go 1 nanosecond here for the step. Okay, and that's all we have to do there. Click OK, and you can place this anywhere on the workspace, on the desktop there. And we're all set. One other thing that has to be done is the circuit needs to be grounded. Okay, this is one thing that LTSpice requires because all measurements are made with a ground reference. So you see the symbol, I click, drag, and drop, and then I wire it, and that's it. Okay, so different sections of the circuit will require separate grounds where you have, for example, DC isolation like a transformer. And I'll show you that as we go on here. So now I'm all set to simulate this. So this is the button to run the simulation. You mouse over it, it says run. Okay, and now what we need to do is select what we want to look at. So I'm just going to mouse over the output of the sine wave generator, and I'm going to click on that and look at the voltage. Okay, that's all we're going to do for this. And you see the circuit is running. And what would we expect to see? A sine wave. So there's our sine wave. We said 1 volt, so it's 500 millivolts peak to peak. So that just shows that the circuit is working. Okay, so we'll get out of that. We'll close that simulation. And we can maximize the workspace again. And let me just reposition. I think that's good. All right, so now we want to do a different type of analysis that we call AC analysis. So you click on that, and this says type of sweep. So this is just the scale. All right, do we want the scale to be linear or decade, which is logarithmic? So we'll just go with a linear scale. And number of points, this isn't that critical. We get pretty good resolution with 10 points. And then start frequency, we're going to say 10 megahertz. And stop frequency, we're going to say 30 megahertz. Now, why 10 megahertz and 30 megahertz? Well, I'm designing this amplifier to work on the upper end of the high frequency band. I'm actually using the amplifier as a prototype for another project. And I'm really interested on matching the impedance and optimizing the match on the higher end. So we still have a 20 megahertz bandwidth here, but I elected to optimize the match and the SWRs on the high end of the scale. You could also go on the low end of the scale and get acceptable SWRs or compromise somewhere in the middle. And we'll talk about that a little further. So there I have my parameters set up. I click OK, and I can place that anywhere I'd like as well. And now we're going to run the simulation one more time. And same thing, we got to pick a point on the circuit that we want to analyze. So I'm going to mouse over the output again and click. Okay, and what do we see here? Well, we see a scale that's in decibels, but what we want to really do is look at impedance. Okay, so I can mouse over the scale. You see that little ruler comes up, and do a right click, and here I can change the type of scan that I'm doing. And we're looking at a Bode plot right now. And what I want to do for measuring impedance is use a Cartesian plot. Okay, now what's a Cartesian plot? Well, it's a fancy word for a plot that is capable of showing two different parameters at one time. In this case, the parameters would be the real part, which is resistance, and the imaginary part, which would be the impedance, whether it's capacitive or inductive. Okay, so we want to look at the impedance, and we've got to apply Ohm's law here, right? If this was a DC circuit, then R equals E over I, right? So basically we divide the voltage by the current. Well, to measure the AC resistance, it's just impedance, but the formula is exactly the same. So Z equals E over R. So we're already measuring the voltage, as you see there, right? It's the same voltage that we got when we looked at the sine wave, okay? But now I'm going to right-click and enter in a simple equation here, right? We said Z equals E over I. So E, of course, is the voltage that we're looking at, okay? And then we just divide. We divide by I. And then it would be I through R1. Okay, so we would have to specify where we're measuring the current, and in this case, it's just the current through the resistor. So that's it. Okay, and now what we have is the real part on the left side of the scale, which is 50 ohms, and the imaginary part, okay, on the right side of the scale, which is 0. Okay, so that's exactly what we'd expect, right? We have a simple circuit with one resistor. We have no reactive components at all. So the impedance would be 50 ohms. So very simple. Okay, this gives us a good baseline to show, yes, it can measure the impedance accurately. Okay, so now we're going to go ahead and create another circuit. Just move that to my left. Now here, we're going to use the same AC source, so we click on sine wave, click OK, and there we are, sine wave generator. And then we right click, and we're going to put a transformer in the circuit. Okay, so a transformer is made up of basically two inductors, all right, this particular type of transformer. So L1 and L2. Okay, and then right click. Then we're going to add a 50 ohm resistor and then wire this. So we go back to our wiring tool, and here, remember, you can go right through the component. Okay. And that's the primary side. We're going to wire the secondary side. So you can see this is very user-friendly. Okay, easy to place components on the workspace, easy to wire up your circuit, easy to enter component values. So same thing here. Okay, we're going to basically mouse over, right click, and enter in the resistance value. We want 50 ohms. And then same thing with our sine wave generator. We're going to mouse over, right click, and we're going to run pretty much the same simulation. So 1 volt, 30 megs. Since we're using Ohm's law and Z equals E over I, it doesn't matter if we use 1 volt or 10 volts, we're going to get the same results. So I just want to point that out. And then again, 50 ohms. Everything's going to be matched to 50 ohms, just like our radio transceiver. Okay, and same thing here. We can move these out of the way, give us a clear view of the circuit. That looks fine. And remember, here's the ground symbol. Both sides of the circuit have to be grounded because they're isolated by the transformer. And they have to be wired in. Just click and click. Okay. And now one other thing. Okay, right now LTSpice sees these two inductors as separate inductors. We have to show that they're coupled like a transformer. So LTSpice has a number of directives, and they're all defined in the help menu when you start to use this for different applications and different types of circuit designs. But right here is the directive, the operation. You see it says Spice directive up there. Okay, you click on that. And to show the coupling, it's the K value. So we go K, right? And then we have L1 space L2. And we put in the coupling factor. Okay, I'm going to just enter 1, which is 100%. Okay, if it was less than 100%, I would use, say, for example, 90%, it would be 0.9, 80%, 0.8, but we're just going to assume 100% for this demonstration. And we're going to talk about how to actually measure the leakage in your transformers and actually measure the K value. And then you can enter the real value right on your schematic. Okay, so we click OK, and that's basically a transformer now. You can see the phase dots on the bottom here that show they're coupled. So now we have to define what the value is here, okay, for inductance. So we're going to use basically the impedance ratio. So just real quick, and we're going to discuss this in greater detail later on, but the turns ratio squared is equal to the impedance ratio, right? So if the turns ratio is 2 to 1, right, we take 2 and we square it, and the impedance ratio would be 4 to 1, okay? Or we can take the impedance ratio, right, let's say 4, and take the square root to find the turns ratio, which would be 2, right? So very simple, right? 2 squared is 4, square root of 4 is 2. So it's that simple. So I can, if I know the impedance values, I can actually enter them directly, and that would give me the impedance ratio. Now we're going to start with a 1-to-1. So, and this is 10 microhenries. This is very close to the impedance of the transformer in my circuit. I think it's 11 microhenries. Okay, so we enter in 10 microhenries. Let's just move that out of the way so we can see it. Okay, right click to get out of that, and then mouse over the device, right click again. Okay, and 10 microhenries. Okay, and we can neaten that up a little bit, move that over a bit. That's fine. Okay, so there's our circuit. Okay, and this time we're just going to run the AC analysis and see what the impedance is from the primary to the secondary. Okay, so we go back into simulate, and we go and click on the command button, and we want to do the AC analysis, which is already set up, as you might recall. Okay, and we click OK, and then we go ahead and run the simulation. So there you see the simulation running. And then what do I want to do? I want to measure the voltage on the primary side here. Okay, and you can see what that looks like when we sweep the frequency from 10 megahertz all the way to 30 megahertz. Okay, and then the same thing. Okay, we want to look at the impedance. Okay, so Z equals E over I. So we click on the voltage, and we can add a simple expression, divide by the current. And this time, it's the current through L1. That's on the primary side. Okay, and we click OK, and we see there's our plot. And now we have to do the same thing, mouse over this scale, okay, and select Cartesian, and click OK, and we see the results. So you can click on the equation, it will give you a cursor, okay, and then we can move our cursor all the way over, okay, and there's a table. It's not in view. I'll have to move this so you can see it. There's a table that shows at 10 megahertz, here's the real part, 49.7 rounded off. Here's the imaginary part. Okay, remember with the resistor circuit, we had no imaginary part, but here we're using a transformer and we have some inductive reactance in the circuit. Okay, in fact, a transformer is fairly complex. with a lot of parasitic effects of inductance, leakage inductance, winding, interwinding capacitance. And we're going to talk a little bit about that. But there's the impedance of our transformer, okay, at 10 megahertz. So again, we take the square root of the sum of the squares, right? So I've already done that here for you, okay? Here's 10 megahertz, here's the real part, here's the imaginary part. We square the real part, we square the imaginary part, okay? We add it, and we take the square root, so that's about 49.82, okay, ohms, okay? And that's what we'd expect. We have a 1-to-1 ratio, okay, on 50 ohms. So we're close to 50 ohms. Now, if we go all the way to the other side, okay, and again, this is a 20 megahertz bandwidth, okay. Now I've just moved the cursor over to 30 megahertz, okay, and you can see 49.9 and 1.3. So again, I calculated at 30 megahertz, you can see here, and it's 49, actually that was 1.3, wasn't it? So let's just go ahead and update that real quick. It's not going to make much of a difference, as you will see. Okay, so now that's at 49.9 ohms, so almost 50 ohms, okay? But we have a small amount of reactance, as you can see there on the high end. So we have a pretty good match, 1-to-1. So what I do when I'm designing a circuit, okay, and it requires a transformer to couple the input, I start with a 1-to-1 ratio, and I'm able to determine from there if the ratio needs to be changed. So what do I mean by that? Okay, so let's go back to our circuit. I can make this a little larger here. Let's go back to our circuit here. Okay, let's say I change the resistance to 100 ohms. Okay, so 50, now we're going to go 100. Okay, and we click OK. Okay, now we have a mismatch, right? 50 on the source, but 100 on the load. So let's go ahead and update the simulation. Okay, and let's just use the center of the scale, which is 20 megahertz, okay, as a reference point. So now what do you see? Okay, we no longer have a match, right? We had 50 ohms to 49.9 ohms on the high end, right? But now we have a 100 ohm load, a 50 ohm source. So you see real part, imaginary part, that's going to be slightly over 100 because of the reactance. So there's a mismatch, okay? So what do we have to do in this case, right? Well, this is a conventional transformer, so we can change the turns ratio, okay? We can click on the inductor, and we can change this and give us a 2-to-1 ratio, right? Change this to 20, as you can see there. Okay, and now we're gonna scan it again. Okay, and our primary is 10 microhenry, secondary is 20. Okay, so you have a 2-to-1 turns ratio. We scan again, and what do you see there? You see 49.9 ohms and 1.98. So you can see the 2-to-1 ratio has transformed the impedance, and we now have a match between the primary and the secondary. Okay, what about a different case? Okay, let's say here we have the load impedance greater than the source impedance, right? 50 ohms compared to 100 ohms. Let's change this to 25 ohms. Okay. All right, and now let's rescan this. Okay, and you see we have another mismatch. Okay, So what do we have to do in this case is change the ratio. Go back down to our circuit, and we change this side back to 10. Okay, but now the ratio is the other direction. So we change this to 20. Now it's 2 to 1. Okay, as you can see there. And then we'll run the scan again. And there you see, we're back to about 50 ohms. Yeah, that would be very, very close to 50 ohms in the center of the scale there. So we're able to transform the impedance from 50 ohms, right, to 25 ohms. We're able to get a match by using a 2 to 1 ratio for the transformer. So that's how a transformer is used to transform impedance. When we look at the complete circuit, we'll go back and revisit this, and I'll be measuring the input impedance, but this time we'll be measuring with the input circuit and the transistors. And we'll see what the results are there. So I hope this helps. I hope this gives you a better understanding of how we use the turns ratio of a transformer. Bring this back up on the screen here. How we use the turns ratio of the transformer, which then determines what turns ratio squared equals impedance ratio. And we use the impedance ratio to do the impedance transformation. And we can do that when the source is lower or greater than the load. Okay? So I hope this was helpful. I hope you have a better understanding of how transformers are used and how we use them in RF circuits to transform impedance. All right, RF Man, thank you very much.